from Dietmar. So we have two talks on two topics from Dietmar Saupe. The floor is yours.
Yeah, thank you. Okay, my screen is not showing.
Sorry, my bad. I just need to start.
Ah, okay. Yeah, thank you very much. Yeah, I will go to slideshow mode in a second. Before I go to my official presentation, I would like to show just this picture here. We had just in the previous presentation talk about reaction times and crowdsourcing. And one of the lessons there was, okay, if the reaction time is very small, this might be an indication that this is from the US and this is what we want and this is what we should accept. While a long reaction time would mean that this is maybe someone from India and we would have to be careful about it if the purpose of the study was to carry out a study in the US. Now here, this is from our crowdsourcing study. It was a very big one that we carried out at JPEG, and we have just the opposite. This is the reaction time in seconds, and you see a big bump here between 2 and 4 seconds, and these are actually the participants who paid attention to the task, thought about it, and gave a proper answer. While the people up here that took less than 200 milliseconds or 300 milliseconds are those, random clickers, that just quickly want to get through the job and, get it over with and get in the cash. A lot of them are from India, actually. That's true. So some of them managed to do this very quickly in spite of the time lag. Okay, that's just an anecdote. So let's now come to the first talk. And that's this one here. I will present. And okay, this is not yet doing it. Let's see. Yeah, so no.
The green arrow will maximize.
I don't see a green arrow now. No, that. No. Oh, there. Okay. Yes. Oh, thank you. The green arrow was hidden. Okay, this is about JPEG AIC3, and so it's a standardization effort that is a group a project. AIC is the group, and I'm the chair of this ad hoc group. AIC stands for Assessment of Image Codecs. And so some of the co-authors of this are John Snyers, who was here previously online, but now it's too late in Europe. I guess he quit. Mohsen Janadele, João Ascenso, Shima Mohammadi, and Thomas Richter, and some more. Okay, the standard is for fine-grained subjective assessment of image quality in the high fidelity range. So let me first say just a couple of words about JPEG and where we are. So when you open up the JPEG page, jpeg.org, you see you come to this sketch that has all these different JPEG projects, 12 or 13 or so, or 15 at this point. So JPEG cares about JPEG 2000, about JPEG AI, so artificial intelligence-based coding, a new thing, and we are in JPEG AIC on the upper right, the blue logo. So JPEG is a joint working group of ISO and IEC, collaborating with ITU on different standards. And AIC has already gone through several parts. Part 1 and part 2 are finished. So part one is about the standard type of quality assessment and BT500 type. And ASC2 is an evaluation procedure for nearly lossless coding. So defining a threshold that says, okay, now the image is perceptually lossless, and now it is lossy. That's finished. And in ASC3, that's part 3, assessment of image coding. We picked up the flicker test from ASC2 and extended it in different directions to come up with this quality assessment in the range from high to nearly visually lossless or to lossless qualities. And the picture there is just a snapshot of the current document. So this is in the stage after the committee draft. So we are submitted this for DIS. We are expecting a 6-month period until we get comments on this version, on the second version of our draft for the standard. And then it should go be published in the next year sometime. And the next stage also would be the part 4 of ASC that has not been officially declared yet, but we are preparing it. And now, right now, there's a call for participation that was just issued a couple of weeks ago and at the 107th JPEG meeting in Brussels. So I would like to focus on ASC3, explain what the standard is for, how it works, and then at the end, point you to ASC4. You might be interested, or some of the participants online might be interested in proposing a solution for a metric to assess the full reference image quality of coded images, compressed images. Okay, so the challenge that was posed for ASC3 is that of fine-grained full reference IQA. This is the cursor showing, I think. Well, maybe not. I guess there's no cursor. Okay, traditionally when you work with the Morse scale, you have those ASC ratings from 1 to 5, and to assess the quality in the very high, at the very high end from 4 to 5 or so, you find that with the Morse you can hardly differentiate the quality levels very well. So that's not covered, and we should look at this in more detail, define new methodologies to have a fine-grained differentiation between images of different quality. And another aspect is that we would like to be better than with the Morse, where you have numbers 1, 2, 3, 4 attached to words or like bad and fair and good and excellent. Something more meaningful in the sense of the J&D scale. So one unit on the J&D scale has a particular meaning, namely how good or how well or how many people can differentiate two images of that delta on the J&D scale apart. So that's a quantitative measure rather than qualitative with the category scale. And ASC2, by the way, is a threshold here somewhere there below 1 on the J&D scale, where the flicker test indicates visually lossless compression. Visually lossless does not mean that it is impossible to see a difference. People can still see it, but the probability that people see it is only 50%. Okay, this is one has to keep in mind when you read visually lossless with a threshold. It does not mean that it is completely lossy. Some people can see it, some people cannot see it, and some of the times people see it or they don't. Okay. So also there's a lack of fine-grained data sets for this high-quality region, and we try to fill this gap. So here's an overview of what I would like to talk about in the standard. We do subjective assessment not with a single stimulus, but with 2 stimuli or even 3, asking which of the 2 has a stronger distortion. And we do this with plane triplet comparisons, so where we show the original images. And then we also do this with boosted stimuli, where we amplify the differences between the 2 test stimuli to make it more accessible to the human visual system. These are then called boosted triplet comparisons, where we show the source and 2 boosted versions, and we show the source so that people can focus more on the fidelity with respect to the source rather than on their preference or aesthetics or so. And then there are same codec and cross codec comparisons, but no cross content comparisons. And we have to then decide in the recommendation, what is the budget for the same and cross codec comparisons, and also the budget between plain and boosted comparisons. And we did some experimentation to find out what our recommendation would be. And then after this assessment, we have to do the data analysis. So I will present the screening procedures based on accuracy, consistency, and order bias of responses, our outlier detection and handling method, and then how to reconstruct the scale values from the plain and the boosted triple comparisons together in a unified model. And then the scales should be given by entire rate distortion functions, or distortion rate functions rather, on the J&D scale. So we do not compute a scale value per stimulus, but a scale value for all of the bit rates in the range that we are testing. At the end, I will talk about the results for our ASC3 data set and our ASC4 call for proposals for metrics. Okay, so start with the plain triplet comparisons, where we have the source image in place, manually toggled with distorted images. So on the right, you see the interface. So there are two distorted images. They're slightly different, and the question is, which image has a stronger distortion? And if you click on the Show Original button down below, these distorted images will be replaced by the original ones. So they are in place. So if there's a little artifact in the teeth of this face, then you can look at this artifact, and when you toggle, you see the original, and then it's much easier to detect this or to verify this artifact in comparison to the case where you have the source image showed side by side, because then you have to move your eyes, the focus, and then you have a higher demand on the short-term memory in your brain. So this is the idea. And the toggling cannot appear or cannot be carried out very, very quickly, because then it would be more like a flicker effect. And so we restricted it to have to a frequency of 2 toggles per second. Okay, and one other point that's mentioning is that we have a not sure option there in order to reduce the cognitive load. Okay, so now the second component is the boosting. Now with the boosting, we have the reference and the distorted image here. As you see here, an example. Left is the reference, right is the distorted image, and I chose an example here where the distortions are quite visible already without any boostings, but just for demonstration here for ease. Then here's the first type of boosting, artifact amplification. What we do here is we take the difference of the distorted image with respect to the source one and amplify the differences pixel-wise in RGB channels separately, all with a factor of 2. Okay, so the difference is multiplied by a factor of 2. This is like a little microscope with an amplification factor of 2. We make everything twice as large. The differences that we want to spot are twice as large now. Okay, there's a limit at 255 of the end of the byte range. So if that is exceeded, we have clipping involved. So the factor 2, we should not enlarge it to 5 or 6 or 7 to make it even more strong, because then we have too many pixels that are clipped. Another boosting technique is zooming. So we can spatially zoom in here. So that means the artifacts are twice as visible. And the third one is the flicker. So we can add the flicker, and I don't know if it's showing it. So yeah, you can see it here also in the projection. It's flickering. So when we do the flicker test, it's the following. So here now we have 2 distorted images, one on the left, one on the right. They are zoomed. There is artifact amplification, and there's flicker. And the question now is, which image has a stronger flicker effect? The flicker is with respect to the source image, right? So you see in the flicker, the stronger the flicker, the larger the distortion is between the coded image and the source. So which image has a stronger flicker effect? These are the boosted triplet comparisons. So triplets because there's 2 distorted and 1 reference, 3 images. All right. Okay. So what can be gained with such a boosting? This is from a previous study we did for IEEE access some years ago. Here you can show on the graph on the right a distortion level on the horizontal axis. So this is kind of a linear scale for the distortion. And then you can see on the vertical axis the perceived impairment on the J&D scale. And it's a linear curve. And we arranged our distortion levels so that the perceptual impairment linearly grows with the distortion level. So the blue curve is kind of what you would get without any boosting artifacts side by side. And then we apply 2 of these 3 boosting types, namely amplification and zooming and no flicker. And then we get the red curve. And we can see the red curve initially is steeper than the blue curve. And that's the amplification, or that's the bonus of the amplification. Per increase of the distortion level, we get a higher increase in the perceived distortion compared to the case of plane comparison. And you can measure it by taking the ratio of the gradients of these 2 curves, the red divided by the blue. And then you have the gain factor here, which is when it's larger than 1, that would mean the red curve is steeper than the blue curve. And so the boosting will give us a gain. And you can see the boosting technique works well for very low distortions and not so well for the higher distortions. So it is suitable for our task on hand where we would like to assess the quality of very high quality images. Okay, so then there was a call for proposals, and after the call for proposals, we prepared the image set that would be useful for such studies. It consists of 10 reference images, and 6 codecs were used, or initially only 5, and then JPEG AI came on top of it. And the visual quality ranges from high to visually lossless. And yeah, so this was published at QMX a couple of years ago. And so how can we reliably assess the magnitude of very small quality differences? So our ASC3 sample dataset took 5 of those images, these 5 here, and 6 codecs. They're listed here from JPEG to JPEG AI at 10 bit rates, and these 10 bit rates correspond roughly to a 0.25 J&D spacing. And this was determined with some smaller pilot tests and then estimated in some way. And then so the total, we had 5 source images and 300 distorted images total. So 5 source images times 6 codecs times 6 distortion levels. That's 300 distorted images. And over a period of 1 year, there were 3 campaigns of crowdsourcing with more than 500,000 responses, maybe even close to 1 million, I'm not sure. And the goal was to reconstruct those 30 rate distortion functions. Okay, so here's a recommendation for the budget. I said we have same codec, cross codec comparisons. We have boosted and plain triplet comparisons. And the recommendation we came up with is 80% same codec, 20% cross codec, and also 80% boosted and 20% plain triplet comparisons. Okay, this is in line with some previous work where in a paper the effectiveness of cross-content evaluations was investigated, and then they also came up with 20%. So these numbers here are not out of the hat, but coming out of some experimentation, the results of which, well, the final results is this, but I cannot show you all the details here. That would be too much for this talk. Also we asked the question, or we investigated whether we should apply the full design of our pair comparisons or triplet comparisons, or just a partial design. The full design means if we have 10 distortion levels plus the source, that's 11 different levels, which we can ask, so 11 times 10 pairs, or for pairs, that's 110 per codec and source. Should we ask all of these questions or only a small fraction of them? And there's some work that suggests, okay, it does not make sense to ask the question, is the level 10 really worse than level 0? 0 is the source and 10 is clearly visible. And so initially we thought, okay, maybe we should not do that and only ask questions where the distortion levels don't have such a big difference. But we found out in our simulations later on, after acquiring all the responses for all possible questions, that it's actually better to ask all questions rather than only a certain part of them. So this is our recommendation, that one should use the full design at this point in time. But that's maybe open for future studies to look at this a little more closely. And for the cross-codec questions, we selected them randomly with preference according to similar distortion magnitude. Okay, to kind of stabilize the resulting distortion rate functions. And then the questions, we have thousands of questions, they come in batches. So one batch is sort of one work unit for a crowd worker. So like 120 questions, that's one batch of questions. And crowd workers would get different batches. So each batch would be maybe taken by 30 or 40 crowd workers, and then others would get other batches. And one other issue that that we recommend is one should use symmetric pairs in each batch. So if you ask the question, distortion level 7 versus distortion level 9 for this source and this codec, same codec, then you should also ask the question, level 9 is left and level 7 is right. So the reverse question, the symmetric one. So that way we can analyze the consistency of the responses. And consistency is a reliability measure, and if people are not reliable, then they are likely outliers or should be discarded or screened. And so every question comes as a pair of questions, and we have then a hand on the consistency. So in our overview, we checked off the first point. The key points for the subjective assessments were explained, and now we can come to the key points of the data analysis. So we look at the screening procedures, the outlier detection, and then we reconstruct the scale values from plain and boosted comparisons in a unified model, and we explain what these models, so these rate distortion functions are. Okay, so first of all, what is accuracy? Accuracy is defined on a batch level. So a crowd worker does a batch, 120 questions, and we assign an accuracy to the responses of for this particular batch of this crowd worker. And if the accuracy is very, very low, okay, then we might say at the end, okay, this batch is not going to be used in the reconstruction, it's discarded. It's a hard outlier detection method. All right, so first we have to decide what does it mean a question is, or the response is correct. Okay, and we simply decided to say a response is correct if the stimulus with a greater distortion level is identified by the observer. Okay, and this applies only for the same codec comparisons, because if we have two different codecs and with some distortion levels, then we cannot say, okay, distortion level 9 for codec for the AI codec is worse than distortion level, or is better than distortion level 10 for JPEG 2000. That's not reasonable. We can do this only for same codec comparisons. Okay, then it is correct. A response of not sure is considered half correct and half incorrect. And then we also have to ensure that we add weights to the responses according to the ease of the question. So we should not punish someone for a wrong answer if the distortion levels difference is close. So can you decide correctly the difference between distortion level 5 and 6? That's a hard question, but between 1 and 9, that's more easy. So if you make a mistake getting 1 and 9 correctly, that should weight more heavily than making a mistake when you give the wrong answer between level 5 and 6. So the weights are just defined proportional to the difference of distortion levels. So distortion levels are numbered from 0 to 10. We take the difference, and then that would be our weight. So here's an example on the right. So here we have two distorted images. One has a distortion level 8, and the other one on the right has 2. So the correct answer would be the left one. That's the one with a stronger distortion. And the weight for this then would be the difference of the levels. So 8 minus 2, that's 6. And then we normalize it by 10, and so it's 0.6. So if the response was left, the score is 1. That's the correct one. If the response was right, the score is 0 or not sure, 0.5, and then it's weighted with 0.6. And then it's all added up together, normalized, and then we have a batch accuracy that is scaled to the unit interval from 0 to 1. Okay, so every batch gets this accuracy from 0 to 1. And likewise, we will get a batch consistency from 0 to 1 using the following definitions. Okay, so now here in this example, you see again the same comparison, but it comes as a symmetric pair, comparing a level 8 with 2 and a 2 with 8. So same images, only in the reverse order. So the correct answer for the first question is left, and the correct answer for the second question is right. All right, so now we give a score of 1 if both answers are correct. If we have it inconsistent, so answers left, left, or right, right, or not sure, they get a score of 0. And all others get a score of 3/8. And then the weights are calculated as before. Okay, why 3/8? Okay, this is easy to explain. Namely, this was chosen such that the following node is true. So a 2 or 3-way random clicker, people that just randomly click either left, right, left, right, left, right, or a 3-way clicker would click left, right, 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 and not sure with equal probability randomly. They all get a consistency and also an accuracy of 0.5. Okay, so if you behave completely randomly as a crowd worker, your accuracy is 0.5, your consistency is 0.5. Now keep it in mind. All right, so now, we already see here the results. This is like a 500,000 responses in a few thousand batches. And for each batch, there's 1 point in the scatter plot. On the horizontal axis, we have consistency from 0 to 1. And on the vertical axis, we have accuracy from 0 to 1. So accuracy and consistency of 1 is very good. So people are very highly accurate. They pay attention, they get the right answer, and they consistently get the right answer. So the top right is good. But 0.5 and 0.5, that's where our random clickers are. And we get a lot of random clickers here. Why do we get a lot of random clickers? Because we did not restrict to the United States. We had it worldwide. And we found out that there are some companies in India who hire people from the street to do crowd working. And what they do is they run scripts on their computers to assess and reserve work on AMT. And so no one else can take it, so that they can take it as soon as the workers come into the office, and then they give it to them, and they all randomly click it through. And often this goes through and will not be punished, but we caught them because of this analysis that we did, and we didn't pay them. Okay, these are the random clickers. Not all of them are, of course, from India. I'm sorry, I don't want to get that misunderstood. Okay, but there are some other artifacts here, or effects. For example, over here, what do we have there? These are the line clickers. A line clicker is one that always clicks on the left button or always on the right button. So what is it? The accuracy will be 50%, right? Half of the time, the line clicker will be right, because it's either the left or the right image that is this has a stronger distortion. And we have in each batch, half of the left answers are right and half of the right answers are right. Okay, so the accuracy is 0.5, but the consistency is 0, right? Because when they always click on the right one, they click the correct answer for one pair, for one question of a pair, and the wrong answer for the other question of the pair. Okay, so these are the line clickers. What do we have down here? Can someone guess? These are people who misunderstood the task, right? They consistently give the wrong answer, right? Yeah, right. So yeah, that's, there are not many, but there are some, right? They misunderstood it. All questions were asked in English. So maybe we got some people from some country and some participants who didn't understand that. Yeah, they understood it the wrong way. Okay, but this is what we're aiming for. And the majority of our responses are from that. You cannot see it here in this plot, but in the next histogram, you will see it. This is a picture for boosted triplet comparisons. And now I'll show you the same for, oh no, before I go to the next pictures. So how can we differentiate now this reliable majority from the rest? Well, we should cut right through like this, right? And a diagonal line like this is one that can be characterized by the mean value of consistency and accuracy. The mean value across the diagonal is constant, right? So we decided just to take 1/2 of the accuracy plus 1/2 of the consistency and threshold that. So that boils down to a line like this, and everything above that line would be accepted in the screening process. Everything below the line is rejected in the screening process. And this is now the picture for the plain triplet comparisons. And there the picture is not quite so dense because we only had fewer responses, fewer batches, and also because PTC is more difficult, and there we have a larger variation. All right. Then also we had an order bias. There could be the case that that people have a bias for the left answer or for the right answer, like a line clicker. And so we calculated this order bias according to this formula, where NR and L are the number of left and right responses. And so we get a number from -1 to +1. And so if that is large, then one should probably not accept that batch. So our screening has 2 parts. So batches with a mean accuracy and consistency less than a threshold should be discarded, or where the order bias is greater than 1/2. And the threshold can be determined manually or automatically by Otsu's method. And here Otsu's method would work quite well. I can show you that later in the results. Okay, now comes the outlier detection, because, where are we? Oops. Let's oops. Something's not reacting right. Okay, so let's just look at the outlier at this slide, outlier detection. So why outlier detection? We had the screening already, but in the accepted batches that we have after the screening, there might still be outliers. So outliers are there when they are significantly different from the consensus given by the reliable majority in the set of the accepted batches. And the consensus then can be defined by the empirical probability distribution of the responses for each of those for each of the questions. And the deviation of a batch from the consensus can be estimated with a log likelihood function. And so what we do here is we swap an inlier batch with the largest deviation with a screened batch with the smallest deviation, until all inlier batches have a smaller deviation from the consensus than the screened ones. So effectively, we're swapping some of the screened batches into the good part, and some the worst members of the good part into the rejected part. Okay, and this is the result here, and you can see here the diamond shapes. Here those are batches that are outliers according to the part that was accepted, and then they were replaced by some of these screened batches that have a better match with the majority here than the red ones. And this outlier detection has the advantage that we do not have to specify the number of outliers or some threshold or something. We can just say, okay, the number of accepted batches is everything that's above here, and then we just do some swaps until the match is as good as it can get. And on this histogram here, you can see our thresholding here. This is consistency plus accuracy divided by 2. And then you have these 2 humps here. So this is a reliable majority. And this is mostly the random clickers here in the center of the scatter plot. And Otsu thresholding does a good job of separating the 2 distributions. And so we are using the Otsu threshold for our data. So the threshold, so our recommendation will not be mandatory to use Otsu thresholding, but it's recommended. I mean, it's optional, and it's not a must. It's not normative. Okay. So this is then the situation for the plain triplet comparisons, and so there, it looks much the same. Okay. So now for the unified model for plain and boosted distortion rate functions. So what do we have? Let's look at the plain triplet comparisons first. So we have here the bit rate, and let's say 2 distortion rate functions for 2 codecs that are under investigation. They are different. They are from a mathematical model. I will get to the formulas later. And so now we just do what is standard in Thurstonian scale reconstructions. So we take 2 stimuli, like here at 1 bits per second, 1 bits per pixel, and here at 2.5 bits per second. One is for is coded with the codec B, and one is coded with codec A, and they correspond to these perceived distortions on the J&D scale. And then the Thurstonian model says, okay, the perceived distortion is a random variable with a Gaussian distribution, and so I plotted 2 distributions that are normal, and they are have the same variance. This is a case 5 of Thurstonian reconstruction. And then from the difference, you can estimate the probability that the answer would be for the question which has the stronger distortion, red or blue. That probability can be estimated from this model. Here, of course, the red one has the higher distortion. Okay, so that would be the situation just with plain triplet comparisons. But we want to have a fine-grained a more fine-grained differentiation here. That's why we have the boosting. And the boosting comes in on the next slide. So here, this is the same picture extended here to the left. And now here we have the boosted versions of the same stimuli. Okay, and so instead of having just one, or instead of having here like a 0.4 J&D distortion, we have a minus, or we have the 2.8 here, and this one has 3.8. And so the perceived distortions have been amplified by some functions that are given here to come down here. And then on this perceptual scale, we again have the same Gaussian distributions. So this is the joint model that we apply. So we have a functional model for these distortion rate functions and a functional model for these boosting transfer functions. And the parameters of these have to be estimated. So instead of estimating for each stimulus one scale value, we estimate the parameters for distortion rate functions and the parameters for the boosting transfer functions. And then at the end, we will output just these functions, a formula for this function. Okay. So these are the distortion rate functions that we tried. 6 different models: exponential, logistic, modified logistic, polynomial, rational, a power function. And then on the right, you have the polynomial boosting transfer functions of degree 1, 2, and 3. There's no constant term in there because the source will be mapped to the source itself. So we start with a linear term, lambda 1 times x. And so the purpose of this all is that these functional models have an advantage with respect to the canonical modeling, where you have one scale value per image independently of the others. So this integrates prior knowledge. For a good codec, it should be that when you increase the bit rate, the quality gets better. So this is an assumption that's built in here. So our models are monotonically increasing. With the higher the bit rate, the better the better the or the smaller the perceived distortion. And it avoids also overfitting. So that's another advantage of this. So these candidates here, 6 candidates for DR functions and 3 candidates for boosting transformations, give us 18 combinations, and we tried out all of them and selected a model by the VQEG information criterion that measures the model performance, or the fitting of the model to the data. Okay, and then for the ARC data set, we found that the exponential distortion rate function with the quadratic boosting function gave us not necessarily the best performance in all cases, but in most of the cases. And since the exponential function is very simple and a natural one, we opted for this one. So we have 2 parameters, alpha and beta here, and then also 2 parameters for the quadratic boosting function. We have to estimate 4 parameters per codec per source. Okay, altogether then 24 model parameters for 6 codecs per source. So when you run an optimization, we have all those cross-codec comparisons. You cannot estimate one distortion rate function at a time. You have to estimate all of them together for one source. That's so the number of unknowns in the optimization is 24. Great, this is then the nonlinear optimization. So we used MATLAB's fmincon function there. We've tried others also. The issue is that you can converge the suboptimal local minima, and the time complexity could also be an issue. So a good initialization is essential. And also you have to have a fallback mechanism in case the nonlinear optimization fails. It could diverge in some cases. So we came up with the following algorithm as a good solution for the initialization. So the first is that we go back one step and actually do the pointwise quality model from plain triplet comparisons. So there we do have one scale value per image and not a functional model yet. That is always easy to obtain, and there's no convergence issue with this. And then we, in step 2, we do the same thing from the boosted triplet comparison. So then we get higher higher impairment values. And then in step 3, we fit this joint functional model to these values that we have there by nonlinear regression. So that would be already a first functional model, a unified one that would work well, but it's probably not the optimal one according to maximum likelihood estimation. So we then use this as an initialization for the MLE and run the optimizer. And if the optimizer succeeds and gets a negative log likelihood that it's better than this initialization, we accept it. And otherwise, we reject it and fall back to the easy to obtain solution that's from the initialization, which didn't happen in our example with the exponential model. Okay, so we finished this point, key points to data analysis, and now just a couple of slides for the results of the ARC data set. So first, the ratio of correct responses. So here you can see how this works for the boosted triplet comparisons and the plain triplet comparisons. So red means the wrong answers, green is the correct answers, and yellow is the not sure responses. And down on the horizontal axis, this is the difference in distortion levels. So 4 means we're comparing, say, stimulus with level 2 with stimulus level 6, higher distortion, 4 levels difference. That should be easier. That should be easier than just 2 levels difference. And of course, you can see now that these curves are nice monotonic here. So that means with increasing, or say with decreasing difficulty here, increasing difference in distortion levels, decreasing difficulty, the number of correct responses is growing, as expected. And we also tested 0 difference in levels. So comparing the same stimuli left and right for certain reasons. I don't want to get into this. And so there everything was, well, we had a lot of wrong answers. Not sure would have been the correct one, really. All right. And for the PTC, we only tested every second level, so to reduce the size of the study, and also because the differences are harder to detect than with the boosting. response times. So these are the response times, the mean response times, also as a function of the difficulty. And you can also see that when the questions get easier, towards 10 levels of difference, the response time is declining, but not very much. Okay. So this is an example for the distortion rate function for one image source 7, the night scene there. And you can see these exponential functions for the 6 codecs that we had tested. We don't say, oops, someone has a microphone on. Test. Yeah, okay, it's better now. So we have these 6 codecs here, but we don't want to raise the impression that this study was done to compare the codecs here, because we did not deeply go into the question of properly selecting the right coding parameters as an expert would have done, experts to JPEG 2000 or XL or so. So this is maybe giving a bad picture for JPEG 2000, but only because we didn't choose the right parameters there. JPEG 2000 would be better, I think, if the parameters would be chosen appropriately. But the output here for 4 of the codecs is written, so we can just summarize it in a short formula, like 5.974 times e to the power minus 1.7 times the rate r in bits per pixel. And okay, then these are the boosting transformations. So they essentially are constant times the distortion minus a constant times the distortion squared. So they go up like this, and and then flatten off a little bit, just like in the graph that I've shown you at the beginning. So as expected. So that's very nice and a success. And if you wonder about confidence intervals, here you can see the confidence intervals derived from bootstrapping the data 1,000 times and for source 7. And you can see that the different codecs are distinguishable also in this figure. Okay, these are then the results for the other 4 source images. I don't need to explain that anymore, I think, and can come to the conclusion now with the ARC4 call for proposals. So we now have this the subjective data, and now the next challenge would be, can you design a metric that would predict the results that we have from the subjective experiments? Okay, so we give out the subjective experiments results, and the images, and people can train their metrics on it and submit a solution. Okay, that should eventually end up in an ISO IEC ITU standard. So the input there would be a distorted image and a reference image, and the output should be the image quality in terms of impairment of fidelity in J&D units. And okay, so we give out the sample data set with the scale impairments as you have seen it here in this presentation. There are 2 documents available. The final call for proposals just came out a couple of weeks ago in Brussels, and the common test conditions also. And this is the URL for it. It's not there yet, but it should be in the next days. Okay, so this is the timeline for it. So in April, this was issued, and you can register in June. And on the September 29th, there's the first deadline for the submission of proposals, including the implementation of the metric. And then we will release an evaluation data set that is only decided upon shortly before, source images and coded images. And we at JPEG, we will then run a crowdsourcing study to find out what the ground truth of this is. We don't know the ground truth at the point of publication. Okay, so then we'll do the crowdsourcing, and but before that, the participants already a couple of days later will have to submit the results of their objective metrics on the evaluation data set. Then we have a meeting in October in Nuremberg where we can view the results and the methods. And on December, we will have the ground truth, and then we will invite the proponents to come to the next meeting again in January 26th in Sydney. And then the collaborative phase starts for the standardization. Okay, so that's it. Thank you very much. And I hope there's some time for questions.
Thank you, Dietmar. Any questions? Microphone there. So.
Thanks for the good talk. I just wanted to ask whether this same thing can be extended for videos.
Can this be extended for videos?
Yes.
In principle, yes. Okay, so we have actually one paper at Circus Systems and Technology, where we tested for video the flicker test, and that was a partial success. That means for some videos it resulted in an improvement of the assessment of quality. But there are also some videos that are very hard for this, and where we get results that would not lead to the conclusion that one should really recommend the flicker test for video. Yeah, but in principle, yes, it works. And let's say for videos with mild motion, it works very, very well.
Okay,
Right.
so just when you show the results for the different regions, right? When you select the crowdsourcing co-workers, normally you select the region as well. Have you have a result for a different region, how they are performing, or
yeah.
it's just all the from the India that you are talking
Okay,
about?
so by region you mean nationality or continent?
Yes.
Yeah, okay. In this crowdsourcing study, we had no limitations. We did not say we only want to have these time zones or this continent or country. No.
So how then you can rational that one? Okay, you have a lot of results over there, and these are the results are majority on the 50%. They are from the India. So this is a very strong statement, right?
Yeah, I mean, there was this previous talk where we learned, okay, the country that we can identify from the system is not necessarily the country that they're actually from. That's one question, one difficulty in this.
All right, so this is the influence of the previous talk that you are talking about.
No,
okay. All right, that's perfectly fine. The second question I have, that one, normally when they see the images, that they download all the images and then they play it, or they real time they download and then play and then mark it.
In this study, we made sure that all the images had been downloaded before they start to give any response. So this was maybe a few seconds in some cases, or 1 or 2 seconds if it's fast. So we made sure that there is no interrupt because of any download issues. But going back to your other question, of course, there are cultural differences between preferences or quality quality estimates. There was a large study presented by Netflix at QMX a couple of years ago. They have the National Video Quality Data Set published, where they have a very large study of just 4 countries, where they selected Japan, Brazil, US, and one other country, I can't remember now. And then they found out the cultural differences. And we have looked at this data set in much more detail than it was published at the QMX. And we found out, and by statistical analysis, that yes, people in Japan evaluate the quality differently from the people in the United States, especially when it comes to extreme ratings. So this indicates that for crowdsourcing studies, it does make sense to carefully look where the people are coming from. So that addresses your question. Yeah, it would be. It's good to document this at least.
Right? Yeah, no, actually, it's very good. Actually, you know that this type of result you can get in our labs as well, because I'm from Scotland. So some of the outliers you can easily detect that one, that okay, they are not performing well. So but that's why we have to need to know that one, okay, from there. But it's a very good study. I think I like it. Right? Thank you.
I see, Cosmin.
Maybe I missed this part, but the rate distortion, I understand obviously why the functions are different per codec, but it wasn't very clear, why is the boosting transfer function different parameters per codec? Wouldn't we expect the transfer between plain comparison and boosted comparisons to have a like fixed factor regardless of codec?
Yeah, a good question. Yes, actually, this was our first try. This is what I proposed. We should have one unique boosting transformation that works for the scale one-to-one. And then we tried it, and then we got results that did not make sense. For some codecs, it worked well, and for other codecs, it was clearly so different from the point-wise reconstructions that we rejected the idea, and that, okay, that, you know, different types of distortions come from different codecs, and they do not have the same, with the boosting, they do not behave the same way, but you know, physiologically somehow. That's, you know, we don't know any explanation that would say, okay, this on this part in our human visual system is responsible for the fact that the boosting with JPEG you know, artifacts is different from the boosting of you know, JPEG 2000 wavelet-based artifacts. Right? No, we cannot say that, but we noticed this, that statistically the fitting is not acceptable. That's why we went to one boosting transformation per codec per source.
Yeah, thank you. There's been a lot of information in the talk, so I'm just going to try to be brief. But one thing that I want to ask, I still internally struggle with interpreting why are we looking at the sub JND to the level of being lower than the visually lossless, in a sense of, all right, if we boost something that we just cannot see, so we have two images that look exactly the same, if we boost them, one of them looks better than the other. Mike, like, why should we, well, how should we interpret this? What does that mean, and why is PSNR not good enough to provide us with the information we want from that? Like, which one is closer to the reference? I feel like in that sense, human visual system is no longer a factor because we know that it's been filtered. So whatever extra information is in there, I'm just struggling with understanding why is one of them better? Because when I boost it, somehow I'm gonna get a little bit more visible things than I would have if I did. Yeah, I'm just really struggling with the granularity. Why do we need to look there? And if it should be even motivated by anything related to physiology or anything like that, because physiology already filters that out.
Okay, yeah, so there's maybe two directions of this question. First of all, why is PSNR not enough? You know, it can distinguish those little differences. They are below the visual threshold. Okay, this was not intended to you know, work towards or produce an objective metric like PSNR. I'm not saying that PSNR does not work there, and I think, and actually PSNR is one of the anchor metrics that we are proposing for JPEG AIC4. So when you propose something with AIC4, you can look at the PSNR, and we tell you how to scale the PSNR values to get JND values. Also, we figured this out, and this is, you know, one possible way, viable and reasonable. Okay, but why are we doing this subjective experiment? Okay, we can measure it, and the people that design the codecs, you know, at MPEG, at JPEG, they are keen on, you know, the finest differences, and you want to, you know, have you know, the highest possible quality and be able to, you know, make, you know, these fine-grained decisions when you design codec decisions at the low level there. And so this is the main application, I think, there. Yeah.
Yeah, thank you. Yeah, I think I understand that. Then the distinction is still sort of, yeah, that's what PSNR is being used for, right? Recently, I don't want to hog this. One more thing is also, I noticed that in that outlier detection, there was basically everything was based on the fact that we already know the answer, which one is correct and which one is not. And we had an awful lot of evaluations of really when we know the answer. I'm just thinking, is there a way of maybe decreasing the number of evaluations to still be able to do the outlier detection without having to run all of these comparisons that are not providing that much value? Have you looked into that?
Are you asking about the scale of the experiment? Can we reduce the number of questions and still get answers?
Sort of, yeah, because I'm thinking if we are looking at a distortion 1 and 10,
Yeah.
Yeah, we have a big weight there. If per person makes a mistake, of course.
Yeah.
The question is, do we even need to run this evaluation? That is sort of obvious, right? Especially if we're looking into small differences. So is maybe having a few of these honeypots enough to provide us with the benefit without actually, taking time from the test?
Yeah. So, okay. So you're saying in our test, we have the full design and we ask each question the same number of times. And would it be possible? Of course, it is possible to say, okay, we ask fewer easy questions and more hard questions. Yes.
Yeah.
Of course, you can do this, and but we have not investigated this. So the only thing that we have investigated is should we should we ask questions that are well, we discarded the easy questions and only kept the difficult questions at different levels, but we didn't differentiate, or we did not look at a finer scale, like reducing the number of questions but still keeping all of the questions. But this can be now easily be done with the data set that we have.
Yeah, that would be easy. Like, I would be really interested in seeing how many of these easy questions are sufficient and how many can be discarded without.
You're welcome to join our efforts and to contribute something there.
Thank you.
I see Patrick.
Patrick.
So yeah, thank you very much. So few comments, questions. So first of all, about we have different perspective on the word boosted, because in our case, when we call what we call boosted is how you can reduce experimental effort. Exactly as you were that Lucas was referring to. So it's so-called active sampling, and how you get once you get something from as a result, how you can what to test to maximize your gain of information.
Yeah.
About outlier detection, I just want to draw your attention towards a model that we developed together with Jingli and Sui Ling a few years back, and we presented here. It's graphical probabilistic model that is exactly finding this type of behaviors that you show in your figure. There is one assumption for this graphical probabilistic model to work, to detect the different behavior, like the horizontal clicker, is that you need a majority of raters which are acting well, which seems to be your case. So I will be curious to see the result of this graphical probabilistic model to detect the outlier on your data. So that may be something we can take offline.
I'm sure I saw the paper, but it does not ring a bell right now. Immediately. So yeah,
it's okay. It's okay. Because it seems you are in the condition where this model could work. So I would be very curious to see that. One quick question: why triplet and not quadruplet?
Pardon me?
Why triplet?
Why triplet
and not quadruplet?
Okay, quadruplets would be like when you use the Maloney type of reconstruction as MLDS. So there you would have two pairs. And two pairs of distorted images, and you would ask the question, which of the pair has the stronger difference in quality? And one can do that, yes.
Okay. I want to drive the attention also towards one paper that we found out, and we reach better discriminability with quadruplet as opposed to triplet. So maybe something to look at.
It can be done. I mean, one problem that we are facing, and I think Mohsen will give two talks on Wednesday addressing this also, is that the screen size that you have available is limited. If you want to put 4 images there, even just 2, there is a problem. So we have the in-place representation of 3 images. So we showed 2 images, but the source is behind it and it flickers.
I see.
Is good. And but then we have the zooming also. Which
I see.
And in itself, because some of the content will be hidden. The screen space and the number of images to show on one screen is an issue that one has to keep in mind.
I want, because jumping back on one comment of Lucas, your last question was about also when you don't know the ground truth, right? because here we assume we have some assumption. We are sure that A is supposed to be better than B. When you want to check the quality of your batch, you could also check the consistency in another way. Let's say if someone tells you that A is better than B, that B is better than C, does he say also that A is better than C?
Yeah.
So the triangular inequality, is it something that you have considered also?
This is not considered in the standard. No, we only have the consistency
Yeah.
between these symmetric pairs, and I think what you're suggesting to consider the consistency when you have three images A, B, C,
Yeah.
you have a single
Yeah.
stimulus, then this makes
And then when you
sense.
don't know what is the ground truth, this can be useful. It's just a hint.
But here we know the ground truth. I mean, whatever the ground truth is, doesn't matter if we have two symmetric pairs. So the answer should be consistent, and that's the advantage. And so we decided to have this as a normative part, that you must use these symmetric pairs in order to assess the consistency correctly.
I would like to extend the discussion on scaling and boosting. Let's say boosting through scaling. Let's say. Is it a use case, like for instance in healthcare, when a doctor is looking at image, they are used to do this type of scaling or boosting things. So is it something that could, let's say, as opposed to PSNR, that this is a use case where you want to know if you use the things in regular scale, this is not what they're going to do, right? They're going to boost the stuff to increase in a certain range the range of a grayscale or whatever. So is it something that you are targeting here? And then it might be interesting to look at this GND behavior once you do these boosting things.
Yeah, I mean, these interactive techniques to boost some small differences are known in the community, in the visualization.
Yeah.
And of course there are relations there, but here we just did the simple version here. I don't understand what particular application you were talking about.
In medical imaging, it's very often that people will do this type of scaling. Okay, so they will boost some in a certain range of the data. They will for visualization purpose, they will increase or they change the gain a little bit, like what you are doing. So, and then I think it's very valid to look at if there is any GND difference due to the codec once you do that. Yeah. Yeah. Okay.
The transformations. Yeah.
If I may answer that, I think the application you are talking about does not have a reference in a distorted. It's one image that is being displayed differently by techniques like histogram equalization, gain, change, etc. This is a case where you know what is your reference, you know the distortion, and you are doubling, for example, the distortions. It may sound similar, but it's actually different, in my opinion. Is there any other question? Because I have a couple of questions for.
Still, you want to know the effect of compression on this, and is it something that becomes visible or not?
We can take it offline, if you like. But any more questions? I have a few questions. Yeah. There are a couple of minor typos. I'll point them to you later in your presentation.
Okay,
it's just.
Thank you. This is the first time that I showed the slides.
Why did you choose 10 hertz and not something where the human visual system is known to be more sensitive, like 4 or 5?
Pardon me?
Why did you use flicker at 10 hertz?
At 10 hertz. Okay, this was the recommendation in JPEG ASC2. So where they used the flicker test to determine the threshold for visually lossless. And also it's related to the sensitivity of the human eye, where the response is highest. So there are some papers
and 10 is the point of maximum.
Well, in that range somewhere, yes.
Because I somehow remember this being around 5. That's why I'm bringing up the question.
Okay, 5 is just half of 10. So 5 is the frequency, right? So and 10 is the change rate. So this is probably the.
So there were 10 changes or 5 changes?
So 10 changes, and 5 cycles. A, B, A, B, A, B, A,
Okay,
B.
so it goes 5 hertz basically.
5 hertz
Okay.
and 10, 10 changes per second.
I see.
Yeah, there was one paper of Stolitska
Yeah,
a long time ago where, and I asked them, what was the frequency exactly? Because it was in their paper, it was not clear whether it was change rate or the frequency. And but I think we resolved this. 10 hertz change rate is roughly right. Of course, this could be studied further and optimized. But there are so many things, and so we didn't do it. It was on the agenda, but
Were these flickers sent over as a video or through some kind of flash animation on the computer? So was there a video created with these frames
the
being
flicker was created in the browser.
in the browser?
Yeah.
Was there any synchronization between showing the undistorted and the distorted, or they could be out of sync?
They were all synchronized.
Because in the demo they were out of
In the
sync.
demo, the demo was those were GIFs. I think they were.
Okay. It was a sync. Okay.
This was not the browser. This was a key point.
I understand.
Keynote.
Okay. So to me, the key question came from Lucas in the sense, why do we really care about determining, and it's a different question whether we can determine in higher granularity between say 3 and 4, where we know there are distortions, so we just don't know which one is bigger and smaller. But the real question is on the range from 4 to 5, where they could all be less than 1 JND. That purpose of the experiment is what I would also like to understand a little bit more. Because to me, it sounds like we're trying to assess the range of where human eyes cannot essentially see, right? So whether it is, once it's not visible, once you're below the threshold of visibility, either we are addressing applications, say, for non-human eyes, right? Robotic eyes, superhumans, or whatever you want to call them, or for some machine consumption application, which I understand. But for human consumption of images, it sounds like once you drop below the 1 JND, that type of determination seems to be artificial.
Yeah.
That's really how I interpret it also, Lucas. And I also have the same sort of question. And I repeat, between 1 and 2 JND to differentiate 1.25, 1.5, that makes sense. Because then you go into the statistical probability between how many people would be able to tell, right? It increases the number of people who tell. But once you are below that 1 is really where I also question the usefulness.
Well, my first QMX attendance was in 2016, and CC Jacobo gave a talk there, and he showed a rate distortion diagram, and he said, it's not a curve like this, it's a step functions like this, and there are only 11 steps that a human can perceive. And I thought to myself, no, this cannot be true. I mean, if you ask one person, and then you might have this thing, but if you ask many people, and you do a statistical analysis, then the correct model would be a smooth one. And it goes below 1 JND, right? So at 1 JND, if you ask the 1 JND question here, this half of the audience would see it, this half would not see it. Now I reduce the distortion, and then you would still see it, but you would not. You can measure it, right? A 40% number of people that can see a difference, 60% cannot. And then I decrease the distortion even further, and now I have a high bit rate, and only Shell can see it, no one else. You can measure it.
But I think this is a difference.
This is the question, right?
Yeah.
So do we reach really the point where there were, because if you reach the point where there was 0, at that point, why would you go anything less? Right?
At 0, yeah, at 0, then you're half of the people will give you the well, let's say half of the people will say left and half will say right, and not forget about the not sure. But when you make a measurement, you will see, okay, 11 voted for left and 12 voted for right, but this one extra person is that's just noise in the data, right? If you ask this thing 1 million times to 1 million people again and again, you would converge to 50-50.
I would say thank you for the presentation. I think this is important.
But if I may extend this, I think it's the difference between GND and satisfies user ratio, and we should and there was a kind of confusion with
Yeah, but there's a good relationship.
yeah, there is a good relationship, as you said, but we should not mix up the two concepts, and it's a bit different. Yeah.
Okay, there's a difference between the JND, which is its threshold,
Yeah.
and the JND scale, which is the measurement of distortion in a unit of one JND.
Yeah.
So one JND means, okay, you can have a threshold there and you have two sides, but 0.8 JNDs is also well defined by this ratio of satisfied users, as it's called. So maybe we should come
Yeah.
to the last talk. Oh, wow, it's already.
I think
Right.
we should, yeah,
Yeah.
go to them. Okay, so next.
Oops. Hmm. Okay, so this is a different topic. Robustness and accuracy of MOS with hard and soft outlier detection. So this is not related or not coming out of JPEG, but it's a joint work with a student of mine, Tim Bleile. And this is the first presentation of it, probably also with some typos in it. So there are outliers in perception experiments, as we have just seen for the JPEG experiment. And so, yeah, perception involves stimuli presented to subjects, and they elicit a response, often in the form of a choice between a small set of alternatives, like ACR. And then the data set is subdivided into subsets, so like one subset per subject. Okay, and then the idea is we would like to identify the subset or the subjects that are outliers and discard them. Or one subset per batch of ratings. I talked about batches of ratings before. So we can have a batch of ratings, and one subject could do several batches perhaps, but with the outlier detection would be per batch. Or one subset for each rating even. This has also been proposed in some of the recent papers. So in this talk, we consider the blue option a subset of ratings that would be classified as an outlier subset is always belonging to one subject, and all the ratings of one subject are in one subset that is either accepted or rejected, or accepted with a certain weight. Okay, then subjects are classified now as outliers when they are significantly different from the consensus given by the reliable majority of subjects. All right. And then the interpretation is that the data on these outlier subsets are likely have not been produced by the underlying perceptual processes that are under study, right? So, and so therefore we should discard them from the data analysis. So here are some examples of outliers: random clickers, spammers, line clickers, subjects consistently giving the wrong answer, subjects trying to fool the experimenter, subjects responding much too fast or much too slow, subjects in wrong viewing conditions, ambient environments, wrong ambient environments, or using wrong types of devices, et cetera, et cetera. There's many different ways things can go wrong. Subjects can be outliers. And so there is many different ways to detect these outliers and how to handle them. There's two types, hard and soft outlier detection. So in a hard outlier detection, we have these subjects coming in, rolling in here from the left, like those 5 dots there, and then they are detected by the outlier detection method. So the red ones are discarded, the green ones are classified as inliers, and so then they go into the scaling and generate the MOS. And there are 3 standardized outlier detection methods like this, BT500 and P910 of ITU, R, and T. In BT500, there's a kurtosis-based method and a correlation-based method. So kurtosis basically looks at the Spearman correlation. It looks at how far ratings are above or below the MOS, and then divides them up according to kurtosis-based threshold. And the correlation based is the one where they look at Spearman and Pearson and take some minimum there and then have a threshold that is adapted accordingly. And similarly in P910, which is an iterative method in comparison to BT500. Then there's the other type, soft outlier detection. That works slightly different. So for each subject that comes in, there will be a weight associated with the subject, and then also a model will be generated that has other parameters like bias or so, and then that together goes into the scaling, and essentially the subjects are weighted by these weights. None of them will be discarded as an outlier, but the weight could be very small, like 0.1 or something, then it would not go into the scaling with a large effect. And the idea is that even outliers might carry some useful information that should be maintained. Okay, and there are several methods that have been proposed. One of them is actually standardized in BT500. It's the Surreal method, which gives us a model of including subject bias, subject inconsistency, and then the quality of the stimuli. There was entropy-based subjective quality recovery, ESQR, robust recovery of MOS, is UREC, RMLE, regularized maximum likelihood estimation, and then a paper from DCC in 2017, it is, not 27, maximum, that was called just generically maximum likelihood estimation. Okay, so that's kind of the ball game. So we have these methods, and then we also investigated on other new hard outlier detection methods. Could be maybe improve this, and we have three new hard outlier detection methods. One is entropy based. Actually, it's not new. It was presented in 2005 by Hay et al. It's entropy based, and so it takes in as input the number K of outliers. So we say 5 outliers should be identified, and then the remaining inliers should have a minimal entropy for the ratings per image. So each image has a distribution of the ACR ratings 1, 2, 3, 4, 5, and that has an entropy. And if the entropy is low, it is just peaked. And so the consensus is high. If the entropy is minimal, then we have a uniform distribution, and there's no good consensus for this image. So a low entropy is good. And so if you sum up all the entropies for all the stimuli, then you want to minimize this. And the search space is the space of all selections of n minus k subjects. So this is computationally intensive, and they proposed a greedy search for this minimum sum of entropies. Okay, here in this work, we proposed another version of a hard outlier detection method, mean absolute z-score. So per image, we calculate the z-score. Right, an image has a MOS, and then a distribution, and we can look at the z-score. So we replace the original ratings by the z-score, and then subjects with a mean absolute z-score above 1 will be rejected. Very simple, very fast, extremely simple. The most simple method of all. Then a little more complicated is the mean negative log likelihood. So we initialize the inlier set to all the subjects, compute the negative log likelihood for all the inliers, for all of the subjects at the beginning. Okay, we take the mean value. There's a negative log likelihood per stimulus, of course, and then take the mean one and remove the subject with the largest mean negative log likelihood. And we iterate until the maximum of the mean negative log likelihood is less than 0.31. Okay, so this is just a definition of our methods. And so now we have 3 new methods, and we have the ITU hard outlier methods, and we have those soft outlier methods. And we now need to know which one should we use, right? And so you go to the literature and find out, for the problem, how we can compare and judge the performance of outlier detection and handling. There is a solution, namely to look at the robustness. Okay, this is what was proposed. So you have those subjects here coming in, and you can do, you can just run the outlier detection, do the scaling, calculate the MOS. That's one trace through this. And then the other one would be to add spammers or to add noise, inject noise in there, or to add line clickers or whatever. There's many possibilities. And so in papers, they added spammers or they added a noise injection. So there's new data, new subjects, artificial subjects that are spammers. And then the outlier detection will have to detect those. And sometimes this works, sometimes it doesn't work so well. You get a MOS, and then you can calculate the difference between the MOSes and quantize it or quantify it with a root mean square difference. All right, you have 10 MOS values without the spammer injections or noise injection and 10 MOS values with, and then you just see, okay, what was the effect of the spammers that we added? And the smaller the root mean square difference, the more robust the method. Okay, this is the proposal in the literature by several authors. But this has two limitations. The first limitation is this robustness method depends on the choice of the perturbation. If you add spammers and compare two methods A and B, A may be more robust than B. But if you add line clickers, it might be the opposite. So which one should you take? Which one is more robust? You don't know. Okay, and actually there's three examples here from the literature. So this is from the DCC 2017 paper from Gili and Chris Bampus. And so they looked at two cases, namely noise injection and added spammers. So noise injection means they don't add new subjects, but they just add noise to the existing subjects. And then they looked at the resulting MOS reconstructions and saw where was the robustness better. And they compared different methods. So SR MOS is, it's a hard outlier rejection, and so plain MOS is a no outlier rejection, and so on. And they found out that when you do the second one here is added spammers, corrupted subjects, then their MLE solution would have a lower RMSD, so it would be the more robust method compared to the Z-score rejection method there. But if you use the noise injection here, there's no clear advantage for MLE. Next example is robustness on the conic 10K data set. And so here in this paper, Serial was compared with ESQR and ZREC. So the same perturbations were used, noise injection and added spammers, noise injection on the left and added spammers on the right. And the lower curve here, the robustness is RMSD here, the lower curve is the better one. So here ESQR was the best one, and here ZREC was the best one. So again, we have an inconclusive result. We don't know which one is really more robust in general. It would be so good to have an to have a way to assess an outlier detection method that works for all possible kinds of outliers, not just spammers or noise injection, but for everything. Okay, so how could we approach this? We need a worst case analysis. And for this approach, we propose an adversarial attack. So in an adversarial attack, we don't prescribe what is the outlier type. We don't say use spammers. We just leave it open to the algorithm to find out what is the most effective spamming strategy to disturb the robustness in a maximal way. And the algorithm itself will find out what the best attack is and how to disturb the data set. So we have a sample data set, let's say of 30 subjects and 20 images. So it's a full design here. So the ratings are displayed in this way in this visualization. And then there's an attack of 5 attackers. So it's essentially a 5 by 20 matrix of numbers from 1 to 5 in an ACR experiment. So these are the attacks, and we will now maybe randomly assign ratings to this attack and find out by how much do these attacks disturb the resulting MOS values. And we can optimize this distortion by some combinatorial optimization method, namely the genetic algorithm that we chose, but you can choose others. Second limitation of the RMSD robustness is the following. A more robust outlier detection method does not say that this is a better reconstruction of the moss, right? It does not say so. Look at this example here on the right. T is the ground truth. So mu T is the ground truth quality of a stimulus. Mu S here is the sample data set. So we have a sample data set from the population. Now the sample will have a moss that is not equal to the moss of the overall population. It's an approximation. It's only a statistical moss. And then when we introduce noise, we have mu N, probably a larger distortion. Now we apply an outlier detection, and we will see, okay, after outlier detection, the two reconstructed mosses are here, and this is a small D2 here, the small root mean square distance between the reconstructions for method 2. For method 1, we have a larger root mean square difference, so a worse robustness. However, the reconstruction here has a smaller error than the reconstruction on the right-hand side. M1 should be preferred, but M2 is more robust. Okay. Now you might say, "Oh, this looks rather constructed. I don't believe that this is relevant for practice." This is wrong. There's a striking counterexample. LPCC is a standard from ITU. When you look at this and compare 7 established outlier detection methods from ZREC to LPCC and look at the effect of added spammers, what will we get? Okay, here's the result. If we look at the robustness here on the right-hand side, you see LPCC has an RMSD of 0.01. It is the most robust method of all of those 7 by far. But then when you look at the accuracy, according to ground truth, we find that LPCC is 0.28 root mean square error, while ZREC is the best, 0.12. So the most robust method gives you the worst moss. So robustness is not the right criterion to make a selection when it comes to outlier detection handling methods. Okay, so this is the second limitation. Okay, LPCC is the most robust, but the least accurate. Okay, so the second goal of this contribution is to assess accuracy instead of robustness. But accuracy requires the ground truth. If you take a data set, conic 10K or whatever, there's no ground truth to it. You just have the data. Okay, so what can you do? The only way to have ground truth is then by simulation. So we propose a simulated data set based on state-of-the-art models from real-world data, so it's authentic. So it provides trusted ground truth to assess the accuracy instead of the robustness. And another advantage is it can generate arbitrarily many sample data sets to allow for statistical analyses. So here's the overview of the flowchart. So we take a data set like conic 10K or VQEG HD3, do the data analysis, and we have used the Serial data set, Serial method. So it gives us mosses for or qualities, BOJ for images J, and biases, beta I, and sigma i's. These are these inconsistencies of the subjects I, and that will provide us the ground truth up here. And then we do a random selection. We select M subjects, from this model and N images from the data set, and simulate the ratings of these subjects for these N images. And so we get a sample data, which is just an M times N matrix. Then we can perturb it with any type of spammer or whatever we use for the adversarial attack, and then do the outlier detection with whatever method we use, do the scaling, and get the Moss estimates and compare these estimates with the ground truth. So then we get the RMSE. Oh, this gives us realistic, trusted ground truth. Okay, these models are accepted; they are standardized, so they work. They have been proven to work. Now, to carry out the adversarial attack, we proposed a genetic algorithm, or that was our first choice. Very simple, nothing special, just a standard algorithm with selection, crossover, mutation, and elitism. So we generated 150 attacks. So these are these matrices of 5 times 20, 100 numbers, integers from 1 to 5. Then we calculate the RMSE, the error with respect to the ground truth, given an outlier detection method that we want to investigate. And we generate 300 generations and stop after 300 generations. That's our stopping criterion. So overall, we generate 300 times 150, that's 45,000 attacks. And out of all those attacks, the best one will be the output of this algorithm. So selection will be roulette wheel selection of the parents, crossover where we randomly swap rows and columns between the parents. Mutation is 0.5% of the ratings of a generation will be changed randomly. And elitism, top 3% of the attacks will be kept in the pool. And then the next new population again will have 150 attacks, all those matrices. Of course, the fitness will be have to be computed, and then this goes into the stopping criterion, etc. Okay, very simple. Then here's an ablation study. Well, is the genetic algorithm really necessary? Do we need it? We could just randomly, we have these matrices, 100 numbers from 1 to 5. We can just randomly assign these values and see what we get with 45,000 trials. And let's do that. So the result is this. Okay, here you see on the vertical axis, the root mean square error. This is the success. The larger the root mean square error, the better the attack, right? And the distribution then here gives us, of those 45,000 attacks, a taste of how much the genetic algorithm is better than the brute force algorithm. It is better by a factor of 3, right? So it really pays off to do the genetic algorithm. This was for the kurtosis-based outlier detection. All right, so here are some example attacks. On the left, the kurtosis-based, on the right, the mean absolute z-score. And you can see that for the kurtosis-based outlier detection, the attacks were quite simple. You're mostly just black or white. That means all ones or all fives. And for the mean absolute z-score, the attack had to be more intelligent to to decide about the rating. Now here's a table for the main result, attacking all the 9 methods that we have in our list. So this goes from the entropy-based, H is entropy, the mean absolute z-score, the NLL, ESQR, and so this is rated or ranked according to the root mean square error. So the top one is the best one. And the bottom one is again LPCC, the worst one. Here you can see the time. It's the runtime for an attack with all of the 300 generations, so generating 45,000 attacks altogether. And this is the root mean square difference. This is the robustness that comes out of the maximization of the RMSE by the attack. FPR is the false positive rate. So this is the rate of wrongly detected outliers in the group of ordinary authentic subjects. And you can now see 93% of the subjects were rejected by the LPCC method. So the attack was forcing the authentic subjects out of the pool. So LPCC is not recommendable, I think. Okay, and ACC is the accuracy of the classification as an outlier. So outliers are the attackers, and the others are not. And RAI is a measure that we can also apply for the soft outlier detection methods. And here you can see that the differences in RMSE are really statistically significant. These are the distributions of what we get for 250 sample data sets. So the numbers here are not just for one sample data set, but the average for 250 runs. And so the best ones are over here and the worst ones are over here. And these normal looking distributions are statistically different. They're significantly different. Okay, let's summarize the findings. So the summary is that we have in the ranking here, the top 3 methods are the new hard outlier detection method with MOS. They're better than the soft outlier method that have a sophisticated subject model. That's a surprising result. And the MAZ, the new one, has the least algorithmic complexity and time complexity and excellent resistance to adversarial attacks. Then come the soft outlier methods, ESQR, ZREC, and Serial in the middle. And then it was a surprise that these are all better than or none of the standardized ITU hard outlier detection methods are they're at the bottom end of the top 10 list. They're even worse than the no opt strategy. No opt means no outlier detection, except everything, right? Just ignore the outlier detection. That is even better under adversarial attacks than carrying out the ITU outlier kurtosis-based or correlation-based methods. Okay, yeah. So this is our result here. And there are, of course, some limitations and some future work. So we only tested one scenario. The ratings were simulated from the Surreal model of conic 10K. Other data sets will give us other models. Other algorithms besides Surreal, like ESQR or whatever, give us a different subject model. Then we only tested for 20 images and 30 subjects and 5 attackers. So these numbers can be changed, and then maybe the ranking will be changed also. The thresholds for HB, MAZ, and MAL, these are the new methods that were determined by trial and error, and one can probably do better. There was one complex outlier detection method, RMLE, that we anticipated to make use of, but the runtime was high, and so we left it aside for future work. One would have to accelerate the computations a little bit to make it accessible to the genetic algorithm. And we only use the genetic algorithm. There's others like simulated annealing, taboo search, and so on. They might also give better results. Then perhaps for soft outlier removal with continuous ratings on the visual analog scale, one does not need to do computational optimization, but one can have a fast differentiable method. One could also follow up a hard outlier detection with a soft outlier detection handling, and then that also raises the question whether this is any better. So finally, what are the contributions? So we proposed a new paradigm for the performance comparison of outlier detection handling methods. It overcomes the limitations of assessing the robustness in the state of the art, and the adversarial attacks with standard genetic algorithms are effective, simple, and fast, and we will make the code available. These are our references, and thank you very much.
Thank you, Dietmar. We are at time, but I think there is enough interest for many questions here, at least from my side. I wonder if we should take them now or leave them for, if people want to stay also online. Okay, let's get started. I saw 2 hands, Patrick and then Lucas.
Check 1, 2. Thank you. Thank you so much for this. Was really interesting, and it's a really, I would say, a novel view for me on the whole problematic. So thank you for that. I'm just also wondering, so basically, if I understand correctly, you tried to make the scores so that they screw up the method as much as possible, right? Like the worst case scenario, what votes would actually bring the methods as far from the ground truth as possible?
Yes, so we hope to have an outlier removal technique that would be robust against any attack, against any any type of spammer or so, and I think that's a natural idea just to optimize for that, and that means making the root mean square error with respect to the ground truth maximal.
One thing that misses, well, at least for me, for my understanding of the whole thing, is how likely it is for this to happen, right? From the real data, when we are, for example, talking about the soft outliers and so on, even though that there is a possibility to drag it further with respect to RMSE from the ground truth, how likely it is that we actually get this sort of data? And that brings me to the genetic algorithm compared to random. Like it's 3 times more powerful, but isn't it also 3 times less likely for this data distribution to happen?
Well, okay, how likely is it that your automatic car runs through a red light? That's highly unlikely, but should you, so you shouldn't take care of preventing for this, maybe.
No,
That's
no,
not the
no.
wrong conclusion. That's not the wrong
No,
conclusion.
that's not what I'm saying. I'm mostly saying, shouldn't that be a factor as well? Because one of your arguments was that we are only looking at when people are spamming this way or that way, and we're not looking at what is possible to happen. And my thing was these methods were coming from the assumption that this is how people would most likely behave when they are spamming. And my mental model is that there's very unlikely that there's going to be a person trying to say, oh, I want to make their data as less reliable as possible. So this is just a suggestion to figure out how likely it is to have this sort of data from a real person. That's all I'm saying. I'm not saying that we shouldn't be testing for it. And that's why I also want to highlight that this is a great view into the problematics.
Okay.
I'm just don't see the, the link to that.
Okay, so now thanks to this, you have a tool in your hand to identify these people, use one of the reliable ones and then filter out the subjects accordingly. And then you can analyze the subjects and answer the question that you have just asked, right? So you could run the MAZ method or the NLL method from 1,000 subjects, and then you would see the rejected ones, and then you look at how they rated. And
Yeah,
then
but
you
if I
can
am,
see, is it mostly spamming or random clicking, or is it some strategy?
but if I am identifying the people that are closest to the worst case attack, and it's very unlikely for them to behave that way, am I not going the other way?
No, I don't understand the question.
Maybe I did not understand the argument either, but yeah.
I think that you may constrain also the type of attack in such a way that they are kind of ecologically valid, that they may happen.
There are no constraints on the attack.
But we
want to be maximally safe. So we want to be safe against all kinds of spammers. So since we don't know whether the spammers will be all random clickers or all line clickers, we have to take into account all possibilities. And there is no other way than doing it this way, I think. I mean,
yeah, but the point is that when you use this genetic algorithm stuff, you may end up in a part of the space of a type of attacks that will.
If I may, Dietmar, if I may, what you are presenting is typically called worst case engineering.
it is, yeah. That's worst case analysis.
Mean square error is typically average case, right? So essentially, are we designing a system for the worst case or for the average case? That's really the fundamental question, or I can say problematic. I'm not saying we should do A or B, but we should first of all understand that this is addressing the worst case. Someone who has maybe a posteriori knowledge of what others voted and engineer their answers to confuse them, right? The adversarial, as you call it, attack. But the question that comes is, how likely is this to happen? If it is a 10 to the -7, for example, case, it's not 0, but it doesn't really matter at the end of the day because the probability of this actually happening to your actual experiment is practically 0, right? This is really the question I'm hearing. And I see one more hand. I just want to make it more interactive, but I saw a hand. We can add one more person to this, if it's relevant to this topic, Cosmin. So, sorry if
I would say
ask any question yet.
I hope it's relevant. So I was thinking on the same lines, like using this genetic algorithm, we're injecting like worst case scenarios that are not likely to occur in practice. I'm wondering if we can sort of like look at what actually occurs in practice using a different way. For example, like can we run a few different outlier detection methods and see the ones that they all agree on, or a majority of them agree on, those for sure are spammers. If like, 3 out of 5 agree that this is a spammer, or then it is. And then we can see what do they actually do. And then we can say in real world attacks look like this. And then we can inject real world attacks rather than like simulated worst case scenario attacks, and then go back and measure them the same way. If that makes sense?
Yeah, that would also be a possibility. But if we have such a worst case analysis on hand here, why should we not use it? I mean, and it's so simple. I mean, the MAZ is the fastest method and the best one, or the second best one. And yeah, and it's in the same spirit as the ITU method. You know, it also, the ITU method, the kurtosis space also counts the, you know, the number of ratings far above and the number of ratings far below the MOS, and then just, you know, has a different mechanism of putting this into the decision threshold. And we just say, okay, if the mean absolute z-score is larger than 1, just reject. And this is so effective. It's astonishingly effective. I was really so amazed that you know, such a simple method beats all the soft outlier techniques and the ITU-based hard outlier techniques. But all your questions are reasonable, I think. Yeah, it's interesting to know what are the real spammers out there? How do they behave? And you have seen some of the pictures that I've showed you from ASC3. There are the line clickers. There are people that always click not sure, not sure, not sure. They gave me this option. I'm not sure, so I just click this all the time, and they should pay me. We will not, but that they expected that. And then there are those that always click on the wrong answer consistently. Those are some types, and then there are the random clickers, yeah. But there's probably more, and with such an approach, we can just put this all under one umbrella and optimize for the best case, not the worst case. I mean, the attackers try to maximize the root mean square difference or error, right? But then when we make a decision, you know, for the method, we decide for the method that gives us the smallest RMSE error, right?
Of the worst case. Yeah, so let's keep the discussion a little bit under control. I think Patrick has the microphone to ask the question now.
Yeah, I want to expand maybe the figure of merit of this method, because some of them have some kind of requirements with respect to number of conditions you look at. So in your case, it's 20 images times 30.
Five attackers and 20.
Yeah, but 30 raters or 30 image, 20 raters. So I know that that was one of the reasons why we introduced ZREC. Was because sometimes if you want to use, for instance, the method of Bumpis, you are kind of constrained with the number of conditions. So the size of your data set that allows you to solve the things through MLE. So it could be a nice dimension also to look at how these methods behave with respect to the size of your data.
So by size of the data, you mean the number of images and the number of subjects?
Yeah. Suppose I have, I don't know, it could be n stimuli rated by m observer, and maybe the result may change, and you may have some different recommendation with respect to this n times m.
Yes, that's a good question. And so that was on the last slide for the future work, but this was more the first time that we investigated this algorithm, and we chose the size of the study, the size of the data sets, so that it matches what's presented in the literature. So these were papers from Netflix, for example, where these were lab studies, where they did have 27 subjects and 20.
Which is typical from SCR studies, but I think it's kind of interesting also to look the things from different perspectives, where, for instance, you have many stimuli but few raters, or the other way around. So
I would like to do this for Conic 10K, where we have 1,200 subjects and 10,000 items. Of course, that will be more compute intensive, but that would be interesting. Yes. So.
Thank you. Any more questions? And again, we can take the questions offline. Thank Dietmar.
Thank you very much for the discussion.
And we adjourn for the day. Tomorrow, let's make sure that if people come in, you know the process by now, okay? You have to repeat it tomorrow. There's gonna be like 2 or 3 of us to accommodate, take the groups in. I would say target ideally around 8 if you wanna have breakfast, or definitely by 8:50 so you are here, so you can kick off at 9, okay? Thank you.